Hello everyone, and welcome to AISC's live webinar, 5 Useful Stability Concepts. Today's webinar is being presented by Dr. Joseph Ura. My name is Brent Liu. I am with AISC's Continuing Education Group, and I will be moderating today's presentation. I want to introduce today's speaker, Joseph A. Ura, PE and PhD. He's Emeritus Professor in the Civil Engineering Department at the University of Texas at Austin. He earned his bachelor's degree from Duke, a master's from Cornell, and a PhD from Lehigh in 1965. He has received numerous teaching awards during his 40 years of teaching at the University of Texas. His research contributions are in the area of stability, connections, composite construction, offshore structures, and elastomeric bearings. He served 32 years, as a member of the AISC Specification Committee and has received the Lifetime Achievement Award and the Jerry Haier Award for Excellence in Education from the American Institute of Steel Construction. And in 2000, Dr. Ura was elected into the National Academy of Engineering for his work in stability and bracing of steel structures. I'm very pleased to have Dr. Ura presenting today's webinar. Dr. Ura, thanks for being here, and I'm going to hand things over to you.
Okay, thank you, Brett, and welcome everyone. We're going to be discussing 5 useful stability concepts. They're listed here. I won't read them, but we'll start with the first one, which is the loss of stiffness as buckling load is approached. Now, Euler developed these famous column formula about 300 years ago. But what's not fully appreciated is that all members are imperfect, and they don't really buckle, they bend when axial load is applied. In this particular slide, we see a formula, and it's a very useful one, in which it says that a member that is imperfect with some displacement delta zero, and this delta zero can be due to the initial curvature of the member. It can be caused by moments, caused by lateral loads in a frame. In all these instances, this formula will give an accurate indication of what the displacement is after you apply some axial load. We sometimes call this term an amplification factor. That is, you take an initial displacement, and as you apply axial load, the displacement increases. This is a really important concept in stability, because what it says is, as the load P approaches the theoretical buckling load, the deflections will go to infinity. And that means that there is going to be plenty of warning prior to an impending problem. This is a plot of the equation. We're plotting P versus the total displacement compared to the initial displacement. The particular imperfection in this case was 1 in 1,000. And as you can see, the stiffness of the member decreases. The slope of the load deflection curve here is a measure of the stiffness. So what happens is that axial load is applied, the stiffness of the member is reducing. That's resulting in larger displacements. And in fact, what this graph shows is the Euler load, which is up at this level, is really never reached, because we're going to start to get some yielding due to the second order effects generated by the P delta moment. In this case, it's located right here at about 85% of the Euler load. Now, as indicated, a very small increase in load as you get close to the buckling load has a very significant change in deflection. In this frame, as shown, if we're at this level, a 6% increase in the load, going from about 0.85 to 0.9, will increase the deflection about 50%. Now that means that when you are getting close to any instability in a frame structure, there should be ample warning that impending disaster is about to occur. And I'm going to discuss one disaster. In the paper, which you can download, there are two others. They're more recent, but I'll just focus on this one, which is the Quebec Bridge in 1907. This is a picture of the bridge taken before it collapsed. At the time of the construction, this is over the St. Lawrence River, it was the longest span double cantilever bridge in the world. And I'm going to read some quotes from a magazine article by Tarkov. That's referenced in the PDF file. This is what happened to the bridge. On August 6, McClure reported to the bridge designer, Cooper, that the lower chords of the south cantilever arm were bent. Cooper was troubled. He wired back with the almost plaintive question, how did bend occur in both chords? Chief Engineer Deans insisted that the member had already been bent when they left the shop. This is a typical situation in which fabrication, construction now start arguing as to what really has happened. McClure insisted that they only began to show deflection after being installed on the bridge. The debate over the chords occupied the greater part of August. Meanwhile, work continued and the stresses on the lower chords grew. 2 weeks later, 3 other chords showed distortion. The bridge was collapsing with glacial slowness, but no one, not even Cooper, appreciated fully what was happening. After another week passed, the crisis should have been obvious to all. A week before, chord 9 of the south anchor arm had been only 3/4 of an inch out of line. Now the deflection was 2 1/4 inches. McClure wrote to Cooper immediately. After Cooper read the letter, 2 days later, he sent a terse telegram to Phoenixville that read, add no more load to the bridge till after due consideration of facts. The floor will be over at 5 o'clock. Deans read it and disregarded. The workers stayed on the bridge. When McClure arrived at 5, Deans met with him and they agreed to meet again in the morning when a letter from Phoenix's field engineer at Quebec was due to arrive, which would support Phoenix's company's position that the chords had left Phoenixville slightly bent but serviceable. Almost precisely as the meeting adjourned, 2 chords of the anchor arm buckled and the Quebec bridge totally collapsed. There are 2 other failures that are discussed in the paper. One's the Marcy, but in the interest of time, I'm going to pass this one up, and if we have time at the end, I'll discuss it. Now, the concept that a member column containing axial load loses its stiffness as axial load is increased is going to be illustrated on a little problem shown here. There's one column and there's one beam that has load on it. The little frame cannot sway, so we would call it a braced frame. And you could read papers or do analysis which suggests that for a frame like this, you might be able to use K factors less than 1. In this case, it would calculate out to 0.84. And so perhaps you think you can put on a load equivalent to about 40% higher than the Euler load. I'm going to define an M sub O, which is just WL squared over 8, the simply supported beam concept. There is a moment connection up at the top, so the gravity load on the beam is causing some moments. The distribution is shown here, which would be a distribution we would typically get from a first order, a normal structural analysis. There's a moment at the joint, there's a moment in the beam, and there's a maximum moment in the column, which at this stage is shown at the end. Now, there's a lot of lines shown on this graph, so I'm going to run you through each one. Vertically is the load P. And so a load of 0 here, Euler here, and then that 1.4, that potential buckling load all the way up here. The graphs show the moments at various locations on this little frame. This curve is the maximum moment near the midspan of the beam. And if we just follow it, we can see that as I apply axial load, the maximum moment in the middle of the beam increases. As a matter of fact, when the axial load reaches the Euler load, pi squared EI over L squared, the maximum moment in that beam is 1/8 WL squared. And in a problem like this, many engineers probably would even just design the beam to carry 1/8 WL squared and not actually take advantage of the restraint that they thought was available at the end. The moment at the location B, which is at the top of the column, starts off at about half 1/8 WL squared, but it reduces as the axial load increases and in fact reaches one Euler load. The moment at the top of the beam is actually 0. What has happened is the inflection point, which was maybe at about the 1/4 point in the beam, has moved. It has shifted as axial load occurs, and at Euler load, the inflection point is in fact right at the top of the column, and the moment is 0. Now, the moments in the column start off at that value based on the elastic analysis, and all this behavior is in fact elastic. And the column load that's maximum increases. It actually decreases a little bit. And then as I get axial loads up to here, in fact, when I get axial loads up to the Euler load level, the moment is a little bit greater than 1/8 WL squared. And that maximum moment has shifted, as we'll see in a subsequent moment diagram, from the end to someplace near the middle. And as you see that the moments are all, both in the column and the beam, are all greater than 1/8 WL squared for axial loads exceeding 1. Now, the two dashed lines represent the moments predicted by that previous formula, in which we are amplifying the moment. And in the denominator, we have P critical. And if you use K equal to 1, the predicted moment in the column is here, which over-predicts. The actual moment is here, and we would predict this. If, however, you use the K factor in that amplification factor, 0.84, then in fact that formula predicts almost exactly what the maximum moments are in the column. Notice that in practice we really cannot get close to P critical because the beams have not been designed for moments greater than 1/8 WL squared. We're going to look at this a little bit more carefully with regard to a moment diagram, which shows how the stiffness is reduced in the column, and what that does is change the moment distribution within the column. This is for P equals 0. When we're halfway up to the Euler load in the column, in all these cases, the load on the beam has been held constant. We can see that the moment, the inflection point has shifted. The shape of the moment diagram in the column is changing from linear to some curvature. At the Euler load, we actually appear to have a pinned end in spite of the fact that we have a moment connection up there. The moment is 0. And then as I attempt to put on higher axial load, in this case 10% above the Euler load, the inflection point is actually moved within the beam, if in fact the beam has the capacity to support this. Usually it would not, so a plastic hinge would form in the middle, and we really could not get a value above Euler. So papers are published that suggest you could take advantage of the restraint that a beam provides to produce K-factors less than 1, but in a frame structure where the beams are carrying load, that's just not going to happen because the beams have not been designed for the amplified moment, notice about a 50% increase in moment, to support a load higher than the Euler load. Now in truss-type structures where there is no load on the beams between the ends, then K-factors less than 1 are a possibility, but actually not in frame structure. Now we're going to shift to the second concept, which is understanding and taking advantage of inelastic column behavior. And again, we're going to look at imperfect columns. An imperfect column, and I'm going to look at the first yield stress of P over A plus MC over I. And in an imperfect column, the moment will be equal to P times delta total given by the formula we discussed in the first portion. Now, a plot of P with different L over R's for first yielding using just P over A plus MC over I produces this solid line. If I choose an initial imperfection of 1 in 1,000, and our cross-section has a depth to span ratio, or a span to depth ratio of 20, and in this case I'm dealing with yield point of 50. So just plugging in the classic strength of materials equation, you get a curve that looks very much like the column curve, which is shown dashed in this case. In the low load or slenderness region, the formula does a pretty good job. In the shorter region or high stress level region, that formula overestimates the capacity of the column. Generally, if you take P over A plus MC over I, and you have that reach yield, you are very close to the maximum load that a compression member can carry. In this case, that would estimate the capacity. There's less capacity by the current spec, and that's because of the presence of residual stresses. Now, when you buy a rolled section, there are already stresses in it, like it or not, and that's due to differential cooling during the manufacturing process. And the concept of residual stresses is usually explained by a series of pictures like this. This might be a residual stress distribution, which shows compression at the top, the tips, and then tension stresses near the junction of the web and the flange. There are many distributions. When I now take a P over A applied stress, those stresses are superimposed on the existing residual stresses to produce a stress distribution that varies over the cross-section. In this particular case, it's shown that the tips have already yielded, but the junction near the web, the average stress, applied stress, is not at yield yet, but because of the presence of residual stresses, some portions have yielded. Now, we know from the stress-strain curve that when portions of the steel or any portion of the steel is in the yield zone, there is no stiffness. That is, E is not 29,000, but E is 0. So that's illustrated by the yellow portions of the cross-section. The green portions are still elastic. And as far as buckling is concerned, buckling is related to deflection and stiffness. The yellow has no stiffness. So in reality, the residual stresses here causing a non-uniform stress distribution leaves a elastic portion of the cross-section that's smaller than the one you bought. And what that does is reduce the stiffness of the cross-section. It effectively reduces I. And that means that we reduce the buckling capacity of the cross-section. Now, this concept is so what? We use the column curve, and yeah, that seems to make sense. But to look at this further, we'll have some practical significance. And also, that concept that there's portions of my cross-section that are useless as far as stiffness is concerned is a little bit hard to swallow. So we're going to do an experiment here. We have a cross-section. The green portion has been manufactured using high-strength steel with a portional limit about 70 KSI. We've epoxied two pieces of low-strength steel that has a yield point of about 40 KSI. These are the stress-strain curves that were measured. Now, in the low stress range on the cross-section, both of these pieces are elastic, and the modulus is 29,000 for the entire cross-section. But if I get stresses on that cross-section that are higher, well then the brown portions will in fact be yielded, and that means that as far as stiffness is concerned, contributes nothing if the structure wants to deflect, or in fact we call that buckling. So we did a test on these. We tested the cross-section that's just the center portion by itself, and we tested this built-up section made up of two materials. But the buckling is going to occur about the weak axis, so the area that's added here in fact adds directly to the moment of inertia. In this case, the moment of inertia is 38% bigger for this cross-section than this one, if in fact all the portions of the cross-section contribute to stiffness. So when we tested a long member that would be expected to buckle at stresses lower than 40 KSI, this member carried 38% or 40% higher load than this one, as we would expect. But when we tested a shorter one will permit higher load or higher stresses. At those higher stresses, the brown portions have yielded. And the experimental test load for both this cross-section and this one gave exactly the same load when the length was short. Now this has some physical significance when you're trying to reinforce an existing column in a structure. when you've been asked by a new owner to increase the capacity. So you might go to a column. The column needs to be strengthened. A common way to do that would be to weld some plates to the flange tips to box the column, which of course improves the weak axis of that original W shape substantially and has a smaller effect in the what used to be the strong direction. If the column was square, we now may have almost equal moments of inertia in both directions. However, if that reinforcement was placed on the original column with significant loads on that column, as I now apply additional load to the floor system, which adds load to the column, the stresses in the interior, in the original W shape, may get high enough to exceed the yield point. And if that occurs, especially if I used high-strength steel for my construction plates, because it was hard to get 36, then as I apply stresses, that original core may totally yield, which will leave just my new plates to resist any stability. In fact, when you study that problem, you find that now the controlling buckling capacity will be what used to be the strong axis, because I only have these two plates remaining to handle stability. Any yielded portion of a steel column contributes nothing to the buckling strength of that member, even though the entire cross-section supports the load. Now we're going to utilize that concept by looking at the column curve compared to the Euler curve and try to understand inelastic behavior a little bit better. We have a tendency to think that the elastic range of column behavior is the low slenderness area, and that the high slenderness area. The low slenderness area we sometimes call the inelastic range, but actually that's not a good way to look at the problem. Inelasticity is caused only by load, not how big the cross-section is. If I have a big cross-section with a small load, the cross-section is elastic and it's very stiff. It's only when I exceed by the AISC column curve with P factors, a P over the yield load, this is the squash load, of 0.35, will I start introducing inelastic concepts. That is, the Euler curve and our current column curve do not line up, whereas they do line up when we have stresses below 0.35. Now we're going to use this idea because I like Euler. And so I'm going to look at this column curve and say, if I took the ratio of our current column curve to what Euler would say we would carry, of course, in the inelastic range, there's a difference. There's a reduction. And we're going to call this a stiffness reduction factor, tau. And mathematically, that's equivalent to what we call the tangent modulus over the elastic modulus. But it's just as easy to just visualize it as the ratio of these 2 points. What this says is the cross-section is losing stiffness. It's not 29,000 anymore. It's effectively something less. I'm going to introduce you to a little bit different way of looking at column design by utilizing that tau factor. And I'm going to illustrate it just with a simple column design first. This is the current method in the AISE specification. There are two formulas, the Euler type, reduced by 0.877, and then what we call the inelastic type. Now I'm going to introduce something that's equivalent. I like that Euler equation, and I'm going to put in the phi factor of 0.9, and then this is just the Euler equation, but I'm going to put in a tau. I'm going to take that AISC equation, divide it by the Euler equation, and come up with a new formula. It's this one here. Now, it's 1 if the load divided by the squash load is less than 0.35, because that means the cross-section has low stresses and it's elastic. If my axial load is higher than 0.35, I'll plug into this formula, and it will tell me how much my stiffness has been reduced. Now, this times pi squared times E is 226,000 times the moment of inertia divided by L times tau. This is the column stiffness formula. I'm just going to do a little column design. I'm going to take a column that has a load on it of 1,030 kips, and it has got a length of 20 feet. It's pinned end at both ends. And what column size is required? Well, of course, if you have an AISC manual handy, what you will do is just enter the column tables with a length of 20 and that particular load, and you would find, if it's a W12 section, that a W12 by 120 will work. Now, that's the easy way, but I want to introduce you to this new way of looking at it because that's going to be important for some other examples I'm going to show. Using this newer idea, I'm going to first calculate. It's always a good idea to know how much load you have on there compared to the yield load. And in this case, I'm going to try this column. And it says that with this load of 1030 on here, my P over Py is 0.584, which is greater than 0.35, and when I plug into that stiffness reduction factor, which, by the way, is published in a table in the 13th edition manual. The new manual has a slightly different formula, but I won't get into that. But what this says is the tau comes out to be 0.764, which is saying that with a load of 1,030 kips, there's some inelasticity on that cross-section which reduces its stiffness by almost 25%. How much stiffness is remaining? Well, it's 226,000 times my moment of inertia about the weak axis, divided by my length, taking care of units, times this stiffness reduction factor, and it comes out to be 1030. It says that this column is okay. Ideally, these things should be exactly equal. However, there's a little bit of round-off error in development. Now, we're going to, this problem, you wouldn't apply this approach because it's easier to use the column table. But that concept is going to be useful in this next concept, which is called the summation of P concept for system buckling. Everything we've done up until this point has been for an individual member. Now we're going to look at systems, more than one member. Elastically, we're looking at a frame in which there are two columns. One has a pinned end and one has a fixed end. There are different load distributions on the frame. In this case, they're both the same. All the loads on this one a lot more load on the right column in this case. And if I plot the total load on the system, which is this axis, versus how much more one is on the other, we see that the distribution of load makes no difference. That is, the total load at which sway buckling occurs is almost constant. It's not exact. There's a slight reduction here. But for all practical purposes, we can say that the load distribution is not important. This structure just needs a certain amount of stiffness, and it makes no difference whether it's in this column, or a combination of these columns to support this load. The summation of P concept is generally shown as shown here, in which for sway buckling of a story, the summation of the story column loads must be equal to or less than the summation of the P criticals, which are really just measures of the stiffness of each column in that particular system. And one way to get these, there are many ways. One way is to just use the alignment chart to get the estimate of the stiffness in each column, and we add those together and compare to how much load is on the system. Now, when I said that it doesn't make much difference whether the load's on one column or much, that's true in the elastic range, but also it is possible that this system, which could sway, may not sway. That is, if I get certain load distributions on there, I can possibly get the members to buckle without swaying. And in that case, each column must support its own load in the no sway mode, that is with K equal to 1. So every column must support its own load with K equal to 1. Now we're going to look at a couple of examples here, one going to be elastic. I've got two columns, one that looks larger, carrying load P, and an adjacent column that has no load on it for simpler calculation. But there are some links connecting these two. These have pinned ends. There is no moment resistance provided by the links. What the links do is just merely require that if the column that's loaded wants to buckle as shown by the orange line, then this column must also bend. The two columns must work together. However, if this column is quite stiff, it's also possible that this column that's shown in green will merely buckle between the links. Now, in trying to analyze this structure, you cannot treat this column as merely being resisted with some springs here of equal magnitude, because the stiffness at this location is different from the stiffness at this location, and there's a lot of possibilities. So we did a little computer analysis in which we are going to plot the load P on this member versus buckling between the ends, the Euler load, I squared EI over L squared. And on this axis, I'm going to just continually changing or increasing the moment of inertia of column B. Obviously, if column B has 0 moment of inertia, there's some capacity that's 1/16 of the load corresponding to the yellow line, because the overall length is 4 times larger than the distance between the links. But as I apply more and more moment of inertia to member B, the capacity continues to increase. The buckling load is a single wave until suddenly, when I get a moment of inertia of 15.3 on this member, the buckling load on member A is shown as bending between the links, and that's the maximum. Increasing the moment of inertia of B further will not increase the level of load I can put on. Now we're going to see if we can predict this behavior using the summation of P concept. In this case, we have the same situation. I've got member A, member B. I want to control the sway buckling load to a level equivalent to buckling between the ends. In other words, I really want to get this sway stiffness stiff enough to let the column A buckle between the links. And that buckling load is pi squared E I sub A over L squared. So this is the load I want to reach. The resistance of the two columns in the sway mode are given by pi squared E I of member A divided by 4L. That's the length. And then similarly for moment of inertia B, notice there's A on both sides of the equation. I can solve for the moment of inertia of B, and it comes out to be 15 times the moment of inertia of A. Wow, that's pretty close to the 15.3. But you say, well, what a waste. I've got to make this so big. I'm not going to do that. I'm going to just choose a moment of inertia of this member and forget about this one completely. Well, what moment of inertia would you need? You would need a moment of inertia of 16 times pi squared EI over L squared, because to reach that load, it's 16 times higher than this. So in this system, I can put 16I in this column, and then I don't even need this. I can put 1I here, and then I need 15 here. I could put 8 here and 8 here. What I'm illustrating is that in order to carry this load in a system, in this system, we need to have a certain amount of stiffness, and how that stiffness is distributed in an elastic situation is not important. If some are in the inelastic region, there'll be an entirely different effect. And that's illustrated in this example problem. So it's a similar looking problem. In this case, it's a little bit more realistic in that I've got load on this column of 439, and I also have a load on this column of 70. You might want to consider this situation being similar to a couple of columns in a mill building, where this might be supporting mainly crane loads. There's some linkage. There's no moment connection at these two locations. And this column may be supporting additional load, roofs or cranes, but it has a higher load. The orientation of the two loads is different. Weak axis in the plane of the slide, strong axis here. And for simplicity, I'm only going to be looking at behavior in the plane of the slide. Well, there are two ways this can fail. This has a small load in the plane of the slide and strong axis. So if there's no sway, as shown by the red, that's the no sway mode. But it's also possible that this column can bend like this, and of course this other column must then bend exactly like that. So let's check out whether these two member sizes, a W12 by 40 for the right column and a W12 by 26 for the left column, will be able to support the load shown. From the AISC manual, if I look up how much phi p sub n I could place on a W12 by 40 with an unbraced length of 8, it'll say you can support 439. Wow, just okay. That's great. But will the system carry the load in a mode shown by the orange curve? So we have to really check the potential for sway buckling, and we're going to be using the summation of P concept with the properties of area and moments of inertia, which is all we need to check out the system. For column A, which is supporting 439, its P over the squash load ends up to be 0.75, much higher than 0.35, so we're in the inelastic range. With that load level, there's significant inelasticity on that cross-section, resulting in a taw factor of 0.414. In other words, it's only about 40% as stiff as if it was elastic. That is, if it had lower stresses on it. The stiffness contribution, I don't want to call this a capacity, it's more a stiffness contribution, is going to be the taw factor times 26,000 times the moment of inertia in the axis of this slide divided by the overall length squared, about 50 kips. Oh, but it's carrying 439. But in the sway mode, I can get some help from this other member. So we're going to see if that member can provide enough stiffness to enable the system to carry the load shown. Column B has a low load. Its stress is less than 0.35 of yield, so it's entirely elastic. And its elastic stiffness is 1 then, 26,000 times its moment of inertia in the plane of the slide, divided by length squared, or 556. This column says I can contribute 556 to the stiffness collection. This column says I can contribute 50 kips to the stiffness collection. The sum of those two come out to be 606, which happens to be greater than the sum of the loads, so this structure is stiff enough to support the two loads shown with the member size shown. This indicates that when one column is inelastic, having another column elastic can in fact really enhance the overall stiffness of the system. This is also shown in that a plot of a frame that we showed previously, except in this case I'm showing a lean-on column. That is, there's a pin here and a pin here. There's also a pin at the top, so the beam is contributing nothing to the stiffness. This is a fixed end, so this is a cantilever column. So you just could say it's got a K factor of 2 if the load is placed entirely upon it. Along this axis is the dimension A, which is just telling us how far this load is from the right column. If the load is applied to the right-hand column, all the load is on it, and you could go to the AISC manual with a K of 2, at least in the 5th edition, and I mean in the 13th edition, and pick out a column that would be satisfactory. And if you did that, you would come out with about 220 kips. Now, if we said that if I put the load over here, the system stiffness is still equivalent to 220 kips, that's not true in this case because our column is fairly stocky and it's capable of supporting loads such that the member can be in the inelastic range. And in fact, that load that comes out of the manual has accounted for the stiffness reduction that occurs due to a load of 220. But if the load is in the middle of this beam, the stress on the right-hand column is not 220. It's only going to be half that. And as a result of that, its stiffness is not necessarily being reduced by any inelasticity, and the system can then have more stiffness than we would think. And so as we take A and we move the load from on the cantilever toward the lean-on column, notice that the exact capacity increases. It does not remain constant as it would if everything was elastic. But there's a change in stiffness of the two members. Very low stiffness for this column when the load is over it, much higher stiffness when the load is over it. And notice that the capacity is very substantial. When when it's near the middle or a little bit past the middle, we start peaking out, because what happens in this zone is that the buckling mode changes from sway to, in fact, no sway of my lean-on column, because inelasticity is starting to form in this member, reducing its stiffness. But it had no stiffness for sway anyway, but it does have stiffness in plane without sway. And so the buckling mode changes. We reach a peak of about, maybe 390. So we can increase the strength of this if we can account for the fact that columns that are stocky and are not stressed up to their maximum possible value as given in the AISC manual can contribute a lot more stiffness to the system when the stresses are low. The capacity, and that's in quotes because we're really talking about stiffness, of an individual column in an unbraced frame determined from an alignment chart K-factor should be only viewed as a contribution to the story buckling stiffness, not as a load limit on that particular column. Now, it's interesting that this summation of P concept elastically also shows up in beams. This is a plot of the total load on a system of two beams. These beams are simply supported. There's a concentrated load in the middle of the beam. And if each beam is loaded the same, this red member is just a link. It's a pinned member that just forces both members to buckle in the same direction. You could go to the AISC manual with that loading, with that condition, and you can predict, or you can use a computer program, that's what this task is, to tell me what the buckling load is. And of course, buckling is for perfect members, and it would say that the buckling load of this individual member is about 1.3 kips. And so the sum of these two come out to be 2.6. The green lines here show the performance of an imperfect beam. I'm not showing the imperfection at the beginning here, but the initial displacement is 0.16 inches. And if I apply equal load to each beam, as with imperfect column behavior, we see a reduction in stiffness as the load increases, and we gradually get to values, since we're dealing with elastic behavior, up to the theoretical buckling load. Notice that if I just put load on one beam, the system, as I load it up, and that load reaches 1.3 kips, it has lost its stiffness, and it would like to buckle. As it tries to buckle, it pulls on this other member that has good stiffness. And of course, trying to calculate that as a brace is complicated because there's both torsion and lateral bending. But notice that the performance is pretty much identical to when we had equal loads on both beams. And so this says that in a system that's tied together, you can add up the potential buckling capacities of each beam and add up the loads on those beams, and the sum of the loads must be less than the sum of the capacities. Individual beam buckling can only occur between the links. they cannot occur with the link. And so the concept works for beams also. We're now getting to the close to the second last concept here, and we're going to have a complete change in direction by looking at the effect of end connection details in built-up columns. I'm going to show a series of pictures here. You might just think of these two columns being two pieces of wood, 2x4s, and they are acting individually. And there's the same load on each one, and just for our convenience, I'm showing them both buckling in the same direction, and this has a little rectangular cross-section with a width B and a depth D, and if you calculate that moment of inertia, you come up with this particular P critical elastic. If I nail these two together, I make the two work together completely, of course I increase my moment of inertia because my depth has changed to 2D. And if you do the moment of inertia, you find that the total load on those two comes out to be 4 times what it was in this. So tying them together is an effective way of increasing the strength of this, the buckling strength of the system. Now what's interesting is that if I merely attach the ends very well to prevent any slipping from occurring just at the end. So there can be slipping all across the rest of the length. The buckling load, first mode, is actually S-shaped, which has an equivalent unbraced or equivalent K-factor of about 0.5 of the total length. The moment of inertia of each member is still the same moment of inertia from this. And the buckling load is exactly the same as the one where I totally connect. Wow, now that is hard to believe. That I just attach the end, and in this particular case, I get the same capacity? Yes, but if I separate these two members and tie them together, the moment of inertia, of course, starts increasing by the distance between here, and so the capacity would increase as I separate. In this case, though, if I did that, I would have no change. But it's interesting, for this particular case, you get exactly the same load. Now, that's a little bit hard to believe. So we're going to look at a video here. I'm going to now show you some test results on a more practical kind of problem. In this case, we're going to take a couple of angles, angles of 5 by 3 by 1/4, long legs back to back. The length's going to be 150 inches, which is in the elastic buckling range. And we're going to vary the conditions at the end and the use of intermediate fasteners connecting these two, and load this up to buckling. The test results are shown in this bar graph, in which the load the double angle carried is vertical, and the number of intermediate bolts we have placed within that length showing. So we've put no intermediate bolts. By the way, there are 2 bolts at the end, at each end of the connection. We can do 1 intermediate bolt right in the middle, then put in 2, then put in 5. The bar graphs represented by the brown means I have tightened the bolts at the end using like turn of the nut method. So I have good slip resistance, And any bolts, intermediate bolts tying the two together, I've just snugged those. The green line, or the green bar graphs, indicate that any intermediate bolts have been fully tightened, like by turn of the nutmeg. And so what you notice is that that doesn't have too much of an effect, even though the AISC equations have two formulas, one for snug intermediate fasteners and one for tightened. So there's a difference, but in reality, for this particular type of test of double angles, there's not much effect of tightening those intermediate bolts. In this particular case, the load at buckling was actually buckling of the two individual angles about the z-axis, because that was the lowest unbraced length. The main purpose that the intermediate fasteners have is to cut down the unbraced length of the individual angle building up the double angle system. There's a group of tests shown here that only reached roughly half the capacity of those that had the end connections tight, and they all have just snug bolts at the end, or in the bright pink case where I've tightened those bolts, but the surface had a lubricant on it, so its slip coefficient was very small. Notice that these members, they just buckled as two individual members. So the lesson from this is that you need to pay attention to the end conditions. The ends contribute mainly to the load capacity, the intermediate capacities slightly. These lines show the LRFD specification values, which are pretty good for the tightened. Now, the AISC equations here, and I'm not going to bother you with those, but I do want to close this section with a very practical application of this concept to my extension ladder that I have at home. So one of the benefits of this seminar is you can increase the stiffness of your ladder. If you ever, when you have a ladder like this, if you ever had the opportunity to put it on a couple of horses, you would find out that this direction is the weak direction and the strong direction is the direction toward the house. And so when you climb the ladder and you shake a little bit, you'll find that it's not very stiff. But by putting these two plates at the end, tying them to the rails, the stiffness is increased about 4 times. And so when I climb my ladder, it's very stiff in the apparent strong direction, but in reality, weak direction. Now, the last topic deals with stiffness and strength required for braces. There'll just be a couple of slides here, and then we'll look at a video of an experiment. The concepts of buckling are shown in this slide, in which I'm plotting the load P versus the stiffness of a spring placed at the center of the column. As I increase the stiffness, the load increases, and I reach a certain point called the ideal stiffness, where further increase in the stiffness of the brace does not alter the performance, and buckling occurs between the brace and the ends, and we call that full bracing and ideal stiffness. Now, this is for a perfectly straight member. When you make the member crooked, you find out that the performance changes, and what we're showing here is the load compared to the Euler load, buckling between the brace point and the ends, versus the force that's generated in the brace as I load up column. And the force increases substantially for the case where the spring stiffness is just equal to the ideal. Notice that I have like 4% of the force, and I'm still 15% away from buckling between the braces. In fact, you will never be able to do that because the member will fail due to inelasticity. On the other hand, if I use a brace stiffness, let's say twice the ideal, the performance is a lot better. The brace stiffness to reach the Euler load between braces is only 0.8%. Computer analyses would show that I really need about 1%. And so in the AISC specification, in order to reach the Euler load, I'm going to need a brace stiffness that's greater than the ideal value. And in the AISC specification, we use 2. So as a simple rule, you have to use brace system stiffness at least twice the ideal value. The brace force is directly related to the magnitude of the initial out of straightness, and you need to design the brace and its connections for 1% of the compressive force if the initial out of straightness is 1 in 500, which is the basis of the AISC specification. We're now going to look at a video illustrating the stiffness and strength. Okay, well, we've covered 5 different stability principles. I hope this has increased your possibilities for innovative and efficient steel design. Thank you.
So we do have a few minutes. We do have a few questions, Dr. Ura. The first question, I want to go back to slide 36. The question is, for the sum of P method, what happens if column B is in tension? Can we increase the load on column A?
Are you showing slide 36 or 35? I think the question must be related to 35.
Yes, I'm sorry.
Okay. So repeat the question, please.
So the question is, for the sum of P method, what happens if column B is in tension? Can you increase the load on column A then?
The answer is yes, because you have an increase in the stiffness of your system with with B. That is, the stiffness of a system under compression decreases, but the stiffness of a system under tension increases. That is, if you try to put lateral load on a system with tension, it will deflect less than if you apply lateral load to a member that has compression in it. So therefore, tension improves the stiffness, compression decreases the stiffness.
Okay. This next question, there's a little bit of a narrative to it, but say we're talking about a typical aircraft hangar roof where you've got identical trusses spanning across the building. The roof is a standing seam deck, and so the diaphragm is created with diagonal steel framing at the truss compression cord. The AISC manual is very clear on how to design each panel of the diaphragm as a relative bracing system, but there isn't anything on checking global buckling to say that every truss is in a sway mode. Is the global buckling mode inherently prevented when you address local buckling in each panel?
The answer is no. Global buckling is always a possibility. And so typically, if you check every member within your system, and let's just say you're checking each frame or each I'll just say set of frames, because there has to be an X system connecting two sets of frames. When you tie those two things together, they can buckle as a unit in a sway mode. And all it means is that the load distribution on the columns of those two frames isn't necessarily important. But you've got to have enough enough stiffness in the systems that can sway together, and whether that's the whole floor or whether that's a single frame, it just depends on your framing system. So typically in a building, when you have diagonals just on a few, the other members, the other frames are leaning on. And in the design of that X system, to prevent overall buckling, when you sum your P, you must always also sum the P on any lean-on frames that are depending on that X system.
Okay. The next question, with the column design example, most of the design, you use a K equal to 1. If the column base is fully fixed, however, can we use a K less than 1?
As I indicated, Ks less than 1 have to be carefully considered, because the stiffness of that column depends on the restraint, and it also depends on the restraint and whether that restraint is provided by a member. In a base that is fixed, you really have potentially a massive moment capacity. And so when you apply your moments, generally your condition is not being deteriorated or increased. In the example I gave with a beam framing into the top, or let's say you have a truss that's being used to restrain a column, and saying you're having almost a fixed condition, well, that truss must be designed then for some amplified conditions and moments, and not just the forces that have been placed on the beam by itself. And so in general, anytime you're using restraint from members that are loaded, you should not be using K factors less than 1. The exception might be at the base of a building, where the restraint is not coming from a laterally loaded member, but from a rather massive foundation.
Okay. This next question, I believe, is in relationship to your last concept on stiffness and strength required for braces. But the question is, the model considered for evaluating the required brace stiffness is having a hinge at the brace point. In reality, the member is continuous over the brace point, and due to this, is there any reduction in stiffness?
Oh, I guess I don't fully understand what's meant by reduction in stiffness. Yes, the column is continuous over, from one end to the other, much like any kind of column. And if I place a brace in the shape that the buckle goes into, there's actually an inflection point. right in the center. So even though the member is continuous, the moment is basically close to zero. When you include initial imperfections, there is a little bit greater force introduced because of the continuity. That's why ideally with a real hinge, the brace force requirement was 0.8%, but computer solutions would show that you needed about 1%. Maybe that gets to the question. I believe I don't fully understand what is meant by the reduction in stiffness.
Okay. I will try to follow up with this individual afterwards. One more question. Do you care to comment on the differences between a nodal brace and relative brace as stated in the AISC manual, and when a brace is nodal and not relative?
Sure. I think there might be some pictures in the commentary that help that out, but basically the classic example that I'll deal with is maybe bracing beams using cross frames. When you place a cross frame in the middle of a beam, that prevents twist just at the middle of that beam. There must be another location where twist is prevented, let's say at the end. And so then there are two locations of nodal braces that define the unbraced length. In a relative system, which is typical of truss type arrangements, if you cut through the unbraced length and you slice through the brace, it's probably a relative system. A relative system defines the unbraced length because it has a length in the direction of the length of your column, and it is attached to 2 points along the length. So a relative brace defines an unbraced length. A nodal brace just merely ensures that 1 point in space is being controlled for either twist or lateral displacement or both. And in order to define an unbraced length in a nodal system, you must have at least 2 locations where neither twist or lateral movement occur.